Hello and welcome to the last experiment of the summer session. Thank you for participating all the way through. And let's talk about it. Today's experiment is on Faraday's law of induction. So what we're going to be doing, or the purpose of the experiment, is to observe how changing magnetic fluxes can create a current, to understand how Lenz's law indicates the direction of induced currents, and to validate Faraday's law quantitatively. So we're going to look at the mathematics of the Faraday's law equation. But we begin by talking about magnetic flux. And magnetic flux is basically the component of the magnetic field that penetrates through a surface multiplied by the area of that surface, or integrated over the area of that surface. And ultimately, magnetic flux depends on three things: the strength of the magnetic field, the size of the area of the surface in question, and the angle that the magnetic field vector makes with the surface, or more specifically, with the line perpendicular to the surface. So there are three things that can change the magnetic flux. Any of these things that can change a magnetic flux will induce a current, assuming there's some sort of coil of wire around or enclosing the surface in question, that any change in the magnetic force will induce a current in that coil of wire, and so induce a voltage, to be specific. The induced voltage is equal to negative N, where N is the number of turns in the coil of wire, multiplied by the derivative of the magnetic flux through that coil of wire with respect to time. So the induced EMF generates a current, which in turn generates its own magnetic field. And so Lenz's law says that the magnetic field generated by the induced current opposes the change in the magnetic flux that created it. And so we talked about this, or we will talk about this in class a little bit, that if the current is, or if the magnetic field is pointing into the coil of wire, and the magnetic flux due to that magnetic field is increasing, the induced current in the coil of wire is going to create a magnetic field that points out. And so that's the basic idea behind Lenz's law. And so in the first part of this experiment, we're going to take a look at that. So what we're going to do is a very simple experiment for the first part. And it's basically one of the ones that Faraday himself did initially, is that you take a bar magnet and you insert it into and out of the solenoid, and you make note of the direction of the induced current as the motion is going on. So as you insert the bar magnet into the solenoid, the magnetic field strength within the solenoid is going to increase, and the magnitude of the magnetic flux is going to increase as well. But then as you pull the magnet out, the magnetic flux, or at least the magnitude of it, is going to decrease. And so how does that affect the magnetic flux, and what is the direction of the induced current in the solenoid? So you're going to try to observe that and try to explain why using Lenz's law. So there's a table in your lab write-up that you're going to set up. We're going to be using logger pro for this part of the experiment. And basically you're going to see, well, how strong a current do you get, and is it in the positive direction, or and is it in the negative direction? And depending on how you set up the current probe in relation to the solenoid, is do you get positive when it's clockwise, or do you get positive when it's counterclockwise? And so what current do you get, and what magnetic field does that result in? And is that magnetic field opposing the change in the magnetic flux that originally created it? So that's basically what you're going to be looking to answer in this part of the experiment. So you're going to be inserting the magnet at different speeds. So again, you notice the magnitude of the induced voltage depends on the change in the magnetic flux. So what do you think is going to happen when you insert the magnet faster or when you insert it more slowly? And the same when you reverse it. And put the North Pole facing in and put the South Pole facing in. How does the direction of the induced current change? And why is it what it is? And again, that goes back to Lenz's law. So that's part one of the experiment. Part two is going to be more qualitative. We're going to put the current probe away, and we're going to work with a function generator and an oscilloscope. We're going to have the solenoid set up to the function generator, and we're going to wrap a wire of n turns around the solenoid. So the solenoid will have its own number of turns, but we're going to wrap the wire into a coil as well with a certain amount of turns around the solenoid. So basically, the magnetic flux through the wire is the same magnetic flux through the solenoid. And so we're going to work with that. And so you're going to set up two tables because we're going to alternate between two different frequencies in this. And we're going to vary the number of turns of the wire. So we'll start with 5 turns, and then we'll wrap 5 more turns so that you have 10. And then you wrap 5 more turns so that it's 15, and then 5 more so that it's 20, and 5 more so that it's 25. You're going to compare with the calculated value of the change in the magnetic flux with respect to time. So how are you going to figure out that calculated value? Well, you're going to use a triangle wave through the solenoid, and by, from Faraday's law, the derivative of the triangle wave is essentially a square wave. So you're going to have a flat positive line followed by a flat negative line corresponding to the induced voltage in the wire. And so the voltage is going from -10 to +10. So the amplitude is 10 volts. And so the voltage is going from -10 volts to +10 volts in a time that's equal to 1/2f. So it's going to be increasing for half the period and decreasing for half the period. So it's going to go from -10 to +10 over half the period, and then from +10 to -10 in the other half of the period. And the period is just the inverse of the frequency. So if the frequency is 250 hertz, the period is 1 divided by 250, or 0.004 seconds. And so it's going to go from -10 to +10 in 0.002 seconds. And so that gives you enough information to figure out how the voltage is changing with respect to time. And then going from the specifications of the solenoid, you should figure out how the current is changing with respect to time and how the magnetic flux is changing with respect to time. So the solenoid has a length of 15 centimeters. Its N is 710. So make sure you understand the difference between N for the solenoid and N for the number of turns in the wire. The diameter of the solenoid is 3.5 centimeters. You'll need that to figure out the magnetic flux. And the resistance with no current in the solenoid is 7.2 ohms. Now, you run some current, there's a decent chance that that resistance will go up. I did not feel it getting hot, the solenoid, but that doesn't necessarily mean that it didn't get at least a little bit hotter. So you keep that in mind when you're doing the error analysis for this part. So that's the procedure, and if you have any questions concerning the procedure, do not hesitate to email me. The lab final is this Thursday. We will not have a lab class next Tuesday. So the lab final is at 9 a.m. on Thursday the 16th. It's going to be due in 24 hours. There are going to be 6 questions. 5 are going to be worth 16 points. It's basically going to be structured like the lab midterm was. The 6th question will have a graph. I'm not sure which of the 6 questions will have a graph yet, but that will be worth 20 points as opposed to 16. So that's the basic structure of the lab final. Again, if you have any questions, do not hesitate to give me an email. Otherwise, good luck. Thank you for taking part in the lab class. Please enjoy the rest of the summer. And good luck with your continued studies. Okay, thank you very much.